Hi everyone, and welcome to the seventh TIA Centre seminar of the academic year, and our first one since Christmas. So my name is Adam Shepherd, and I'm a postdoc here at the TIA Centre. For those of you that are new to our seminars, in these seminars we aim to invite researchers from across the globe to present new and exciting work. So today I would like to introduce Dr. Gabriele Campanella. Gabriele Campanella is a senior computational scientist in the lab of Thomas Fuchs at the Icahn School of Medicine at Mount Sinai, focusing on computational pathology. Dr. Campanella obtained his PhD at Weill Cornell under the mentorship of Dr. Fuchs at MSKCC. In his graduate work, Dr. Campanella focused on the development of clinical-grade decision support systems for cancer detection from histology slides. In his position at Mount Sinai, Dr. Campanella is now focusing on discovering novel morphology-based computational biomarkers and combining them with other medical data modalities with the goal of improving our understanding of disease and patient outcomes. The title of Gabriele's talk is Pathology Foundation Models at Health System Scale. So thank you very much for joining us today. And yeah, we're really excited to hear your talk. So please feel free to start when you're ready.
Thank you very much. Thank you for the presentation. Yeah, my name is Gabriele, and as Adam mentioned, I work at Mount Sinai here in New York City with my in Thomas's group. He says hello, by the way. He was excited to hear that you invited me to speak. Yeah, I'm gonna talk about some of the work we've been doing here at Mount Sinai. And as usual, I tend to start with, the data. I'm not gonna go into as much detail because I think everybody's probably comfortable with pathology. And yeah, you mentioned, but yeah, feel free to ask questions at any time and stop me and let's have a nice conversation. So digital pathology, very complex, hard data modality to deal with, super high resolution. I can really go and see nuclear detail at 40x, and these, are centimeters of pieces of tissue. So you have hundreds of thousands of pixels, and it becomes very challenging to work with this type of data. But it does bring out the possibility of analyzing these slides with computational methods. This is where computational pathology comes in, and it can be applied in many different ways and parts of the clinical workflow, from quality control the way down to recommending treatment and stratifying patients and so on, and more towards the personalized medicine aspect. And to do that, usually we build predictive models. And one of the most common strategies to do that is to take this huge slide, chop it up in little tiles that are more easily analyzed with the current methods, and then train a tile-level encoder somehow, freeze those models, extract features, and then train in a second step an aggregator that takes these features and then aggregates them to obtain a slide level representation, and then you can train a slide level model. And this is, I think, the most common strategy to analyze pathology slides nowadays. And this is where there is a clear potential benefit of creating a pathology foundation model. Because if you have a good encoder at the tile level, you just have, you're left with training the aggregator, and the encoder usually is what takes up most of the resources at training time, because really you have to, in most cases, train on and really go at full resolution over the entire slide. And that's what takes a lot of the resources. So it'd be very beneficial for the field if there was a pathology foundation model. And as of course, this has been met with a lot of research. So this is just in a few months, or well, maybe at this point, about a year of work of trying to build foundation models. And of course, I'm going to discuss the last one, which is our effort here at Sinai. But I think it's also important to see what's happening out there. And this stress to be sort of exhaustive, but if you know of other works that we felt to include, please let me know. And what I like to put attention on is a number of tiles, here in millions, number of slides used, the origin of the slides, so what type of data sets they're using, and how heterogeneous this data set is with the organs, and also the strategy. As you can see, a lot of this relies on self-supervised learning, or actually most all of it. A lot of it relies on TCGA. There are several rows where it's not TCGA, and but this mostly comes from either Harvard, MSK, and now Mount Sinai. And if we look at the number of slides, for the most part, relatively small number still, and also a million of tiles, not as large compared to, you know, the normal computer vision literature. So I want to focus on, oh yeah, I should mention the one from Vorontsov 2023. There's an asterisk there because it's really, there's this sort of more of a white paper, I guess, not really explicitly stated how many tiles they use. So we put an asterisk based on their description. That's our best guess. That comes from Page with data from MSK. Okay, so far there's a lot of work, but I think there are also some pitfalls that all the works, including ours, share, and I'll talk more about it later. But I think these are the use of self-supervised learning algorithms, or the reliance on that, pre-training on smaller data sets, and specifically talking about reliance on TCGA for pre-training, but also for evaluating performance on non-clinical downstream tasks. And one thing also I want to mention is that a lot of these works come from companies, and these are not necessarily academic efforts, which means that more likely than not, embedding models, at least their best ones, probably not going to be shared. And it's definitely a pitfall, I would say. Okay, so the first thing that I mentioned was that of self-supervised learning. So, I mean, I don't think I need to introduce this, but the training strategy is a strategy where the data itself provides supervision. So does not require annotations. All kinds of strategies are now available. You know, a field that on its own really exploded. It also led us to large language models being what they are today. I guess one of the questions that I think is important to ask is whether self-supervised learning is right for pathology. It seems to be very good for natural images, like ImageNet or internet images. But if you see at a lot of these examples, there's usually a clear object in the center that is the main focus of the image. And I think still a question whether it is the optimal way to train a pathology foundation model. And we can think of dealing with this question from methodological standpoint, but we can also do it experimentally. And I guess that's what we do. Or part of what we do. So we want to, in this project, which is a work in progress, we want to benchmark these self-supervised learning algorithms, understand if they're really appropriate for pathology, how well they work. And we want to do so with a very large, or the largest so far, pre-training data set that is also clinically relevant because it's clinical slides coming straight out of the health system. And also clinically relevant tasks, also tasks that with slides that are also just coming out of the health system, day-to-day slides that the pathologists actually review, and hopefully release these models that we train somehow to the research community. And that is also definitely a work in progress, but so far our idea is that we will have some sort of API that people can use to get embeddings back. But I will touch on that a little bit later. So the first thing I'm gonna start with is the data set. I want to introduce a little bit of why it's relevant that we're here at Mount Sinai, that Thomas has moved to Mount Sinai. It's the largest health system in New York. It has 8 hospital campuses, over 400 ambulatory care practices. And it receives more than 4 million patients every year. And whenever there is tissue involved that a pathologist has to review, we have a centralized pathology department. And they have started scanning relatively early on and started quite aggressively. So this is a plot of their clinical scanning effort. As you can see, started very slowly in 2020, also with the help of the pandemic. But then steadily it reached this capacity of about 6,000 slides a day for scanning, and we've been doing that for 3 years at this point. And this is actually 40% of the volume that they see in the pathology department, just because they didn't have enough scanners. But that is actually now changing. We have now full capacity, so that slope is going to increase going forward. That's cumulative, I should mention. But this is the clinical effort, very different from what you can do in research. Because with this, FDA-approved systems, it's all siloed. They wouldn't want you to get the data out because probably they want to sell you their products. But with a very strong push from the institution, we were able to get our data out. And then my job was that of building the pipeline to get the data out and then to make it available for research. So we transfer it to our HPC cluster, and then we de-identify the slides so that they're available for everybody here at Mount Sinai. And this is just the overview of this pipeline that I developed. And as you can see, we are over 1.2 million slides to date. And so I'm very excited to having been part of this process and being able to release the data to researchers here. And of course, as the computational pathology group at Mount Sinai, we take advantage of this by trying to run these large-scale experiments. And when I started this was over a year ago. At this point, I defined this cohort for pre-training, consisting of over 423,000 slides. And this, again, is everything that we had at the time. So it really encompasses every specialty and all the organs. And at that point, it was about 600 terabytes. on disk. These are just compressed JPEGs at the end of the day, and H&E slides. So I should mention. In terms of pre-processing, what I did at the time was to pre-tile the slides just to speed up I/O training time, and at 20x, so 0.5 microns per pixels, and this comes at about over 3 billion tiles. And in terms of the space on disk, it's over 100 terabytes. The difference, of course, comes down to the fact that the original slides have 40x, so tiling at 20x, you see it's a smaller footprint. And then in terms of how to set up the training, I decided to create these pseudo epochs to track training, just arbitrarily. I chose to create them as 65 million tiles and sampling 1/5 of the slides, so that every 5 slides you go through all the slides in your data set. And I did some sampling of the tiles per slide based on the organ type, so that I would get more heterogeneity there. And just to compare with other works in the computer vision literature, we also include the ImageNet epoch equivalent, which is 50.7. So every pseudo epoch that we have is 50.7 ImageNet epochs, roughly. Here in this little plot, I compare the number of tiles of other works, and we're proud that we're pushing the boundary of what's been done. Very quickly about the organs, just want to show you, we didn't spend a lot of time necessarily curating the organs. You can see our first one is autopsy, which can mean many things. This is just what we get back from the LIS, and just try to balance things out. As you can see, a lot of things here are sort of also repeated, but analyzing and putting things together come to 42 organs, and that should be representative of every single thing that really just comes to the clinic. So pre-training data set, first important thing. Second important thing, the downstream tasks. And so this is what we have shown so far in what we showed in the archive release. And this is maybe the hardest part. So in order to get these clean cohorts, really what's behind is tons of meetings with pathologists. I meet with them several times a week. Very deep knowledge of the LIS and how pathologists at our institution sign out cases per specialty. And so based on that, we are curating these downstream tasks for various tasks. And I think it's one of the most important things about the project. And it's just one slide, but there is a lot of work behind curating this, and we are adding more and more, hopefully in the future. But so far we have some detection tasks, for example, in breast cancer, IBD detection, and then some biomarker tasks, for example, ER prediction from H&E in breast cancer, and EGFR mutation prediction in lung cancer. And we have 2 data sets, 2 cohorts of that, one from MSK, one from Mount Sinai. And then an outcome prediction task also in lung cancer with data from MSK.
So can you hear me okay?
Absolutely.
Do you mind if I ask a couple of quick questions?
Of course.
We've got a question from Craig Miles in the chat who asked, is the choice of utilizing 0.5 microns per pixel as opposed to 0.25, for example, purely computational? So using 20, 40x, sorry.
I think two main reasons. One is that that is what most people do. I think all the works that I've shown before are all done at 20x. And the second thing is this our first go, and at 20x you already get over 3 billion. And so in part, yes, computational. But in the future, of course, we also want to go for the X full resolution. And we have, I'm gonna say a few words about that later.
Cool, thank you. And just a follow-up question for me. Well, a separate question for me, sorry.
Mm-hmm.
So are these all these downstream tasks, these 6 different data sets that you've got here, are these completely separate? They weren't used for training, well, for the pre-training?
Correct.
Yeah, brilliant. Okay, thank you.
I mean, I don't think it probably makes a difference, but you know, just for yeah, to be correct.
Thank you.
Thank you. Okay, so we have a pre-training data set, we have defined some downstream tasks, and the next is I want to discuss how we perform the downstream training, our strategy, which should reflect what people then would use these foundation models for their own research, which would be the models are frozen, you extract the features, and then you train some sort of model. Importantly, we decided to go with gate and meal attention, which is just basically a linear combination of the features to obtain a slide level representation. And this attention, which is the weight for the weighted average, is just based on each tile. So it does not include any sort of correlation with other tiles or topological spatial distribution of tiles on a slide, none of that, which makes it, I think, a good method to use when you want to look at the representational power of these features. And so the closest thing to linear probing that you can do, I think, with pathology slides. And then to estimate the generalizability of the models, we like to use Monte Carlo cross-validation, and we do 20 rounds. So that's what we do. In terms of baselines, what we have included so far are models pre-trained on ImageNet. So we have a truncated ResNet 50, which is popular choice from Faisal's lab, and then just a full ResNet 50. Of course, we would like to include more baselines, but I'll discuss that later. And the training, just to give you a pictorial view, is like this. We freeze the encoder, which could be either one of the models that we train or a baseline. We get our feature vectors and tiles per slide of features. Split that in 80% training, 20% validation, train on the 80%. And this is done at the patient level. Training on the 80% and then check the validation. Usually we just use the last AUC after training. We do this 20 times with 20 random splits. Okay. Time for the results. These are the results of pre-training. And so far, we've done, that we're listing on the archive, we have a Dino model and a master autoencoder model. For the Dinos, you can see it's a VAT small model. And with the MAE, we were able to do a VAT large. These two methods have very different performance and the memory requirements. So Dino much more memory hungry due to the multi-crop that they perform. So same GPUs, but with the Dino, we have a batch size of 90 per GPU, and but we could only do a VAT small with that batch size, and also use 12 of them, and that took 17 days out. On the other hand, with the MIE 180 per GPU, less GPUs, larger model, but still take about the same amount of time to do, and double the pseudo epochs, as you can see over here. So quite interesting. So what we do at this point is we take our favorite checkpoint, which could be the last checkpoint, usually. And then we do what we discussed before, which is now our frozen encoder is maybe the last checkpoint for the VAT small, and we do this thing, these 20 rounds of Monte Carlo cross validation for every one of our tasks, and we get this, which is already quite interesting. So this is the AUC validation, the training of the validation of the GMA for every clinical task, and just plotting the validation AUC. And a couple of things to note here. One is that Dino performs much better than everything else. MIE doesn't perform much better than the image and pre-trained models in many cases. And ImageNet, I mean, we knew it already, but sometimes you get quite good performance already out of that. But we can do better with Dino, for example. And this is true across all tasks except the outcome task, which is, very hard, and that it's something that has not definitely still very open scientific question, how to predict outcome from pathology.
Nice, that's a good question, Gabriele.
Yeah.
Just wondering, so I mean, such a big difference between Dino with VAT small compared to VAT large and MAE. Did you try the VAT large with, VAT small with MAE as well? Just wondering if it's got anything to do with the pre-training method rather than just the network used.
We did not.
Okay, fair.
I mean, yes, there is the possibility that that could influence things, but you would think it's the other way around, in the sense that the more data you have, the larger model you need.
Yeah.
And I think I'll come back to that in a second.
Sure, thank you.
Yeah, no, thank you. So we can summarize all these results. And by the way, since Dino performs best, I'll focus on that going forward. But we can summarize all these results by taking, as I mentioned, the last validation AUC after training. So this point over here. And then we can plot that separately, because it's also interesting to see not only the last checkpoint of pre-training, but also how during pre-training this validation AUC performs. Basically to see whether you need to go all these 25 pseudo epochs, or maybe you can stop early, for example. So we do that. We do that with previous checkpoints as well, and we get this sort of behavior where in many cases, after 5 pseudo epochs, you get quite good performance, and 5 pseudo epochs incidentally is a whole pass through all the slides. And so because of this, the question comes whether maybe less data would be enough. You really need 400,000 or potentially more slides, and you know, over 1 billion tiles. So to try to tease a little bit of the answer there, we created other data sets. And I think maybe this is not on the archive, but you know, it will be in the next iteration probably. And we try to I mean, in best case scenario, you would change the number of tiles and the number of slides independently and see the differences there. But you know, these experiments are quite resource intensive, and this is not the only project that I have going on. So I have to really, we have, as everybody, probably limited resources. So we created a 50,000 slide subset with 400 million tiles and 100,000 subset with 400 million tiles, basically. And so we change number of tiles and number of slides at the same time. So it becomes harder to say what makes the difference, but I think it's interesting to see. And I plot the results on ImageNet epochs to visualize exactly how many, you know, optimization steps, I guess, or how many tiles we're seeing. This is maybe a bit chaotic, but we can summarize this further by taking best performance on each plot, and we can see we can obtain this plot where we see that you know, not a huge difference between the 50K, 100K, and the full 420K. On average, the 423K pre-training data set does yield better results, but it's not by a lot. And you know, does this mean that we don't need 423,000 slides? I don't know. I think part of it could be that we're using a VIT small and we're saturating the capacities of this model. But I'm going to discuss this next, because you know, we did spend a lot of work on this, but there are still a lot of shortcomings and a lot of things to keep working on. In fact, we weren't even going to release this because usually we just submit, you know, papers to like journals or conferences. But you know, with the heating up of the field and everything that ChatGPT, you know, this acceleration of you know, research, everybody was submitting, and I think it is important also to I think these are interesting results that could also maybe steer research also for other groups in terms of lessons learned, what works, what doesn't work. So I do think it is important. There is a benefit of this heating up and this acceleration of the field. But yeah, so I'm digressing. But yeah, shortcomings. I did say we have all the organs, but some of the specialties are underrepresented in our data set because, as I mentioned, we only do 40%, or we used to do 40% of the volume, which means that, and it's based on specialties. So, for example, breast cancer, almost everything is scanned. Lung cancer, and not a lot is scanned. So, and that is you know, something that came from the pathology department. They chose somehow what to scan and what not to scan. So we do lack some tissue representation there. But interestingly, even though we don't have a lot of lung slides, we did have a lot of lung in the tasks and in the downstream task, which actually performed quite well. So that is a side note, something interesting. We use 6 clinically relevant downstream tasks, but 6 is not a lot, and only 3 anatomic sites: breast, GI, and lung. Lack of baselines. It would be great to have publicly available models as baselines, and models also from other groups. We train a small model nowadays. A BIT model is tiny compared to what people use. And yes, we only did Dino and MAE, but there are lots of other SSL algorithms, and it is not public. So actually in the archive, we have a link to GitHub where we wanted to share some of the code, the hyperparameters, and all of that. Turns out actually was behind the firewall of Mount Sinai. So in the next iteration, we will have a properly functioning link. We didn't realize that our enterprise GitHub was not accessible outside the firewall. So I guess, yeah, we have to improve on that. So all these shortcomings lead me to future directions for this work. It is the largest pre-training data set out there, but we want to improve, make it larger. At this point, we have over 1 million slides. Why not take full advantage of that, which means larger cohort, more tissues, now that we scan 100% of the volume of pathology. But that also comes with some difficulties. As I mentioned, 3 billion tiles is already quite challenging and something that not many people handle. Of course, we want to increase that. So we are thinking about better sampling strategies that will take advantage of the representations that we've already learned to get a better representation in the future. 4EX also comes into picture as well, and so yeah, we want to improve on the pre-training this dataset size. We want to improve on the clinical task side, more task types, more tissues, and the benefit of what we're doing is that it's clinically relevant, but then it cannot be compared to anything else, which is a bit of a has its issues of its own. So we also want to include public tasks so that it can potentially be compared. And as I mentioned, this is maybe the most challenging part of the work, but we keep including more things. So for example, it would probably be present in the next iteration, but we have breast HRD prediction task, and we also have HCC outcome prediction from immunotherapy task that for which we're already working on, and we have results on that already. And we want to do this more systematically as well. For example, having a cancer prediction for every cancer type, for example, or a pan-cancer task. Another one is larger models. As I mentioned, we sort of see a plateauing with this VIT small, where 50,000 slides, and you get a model that does not do much worse than if you train it on 400,000 slides. So maybe that is due to the model. We use 21 million parameter model. The largest model these days is from Google, VIT 22 billion. Of course, these circles are not to scale, but yeah, I think it's worth to explore larger models because we see the scaling laws in the language world, and also in the natural image computer vision world. So it makes sense that these would also hold true for pathology. And we've actually, started doing that. So here is a model, a VIT base now instead of VIT small. It's still, I guess, on the smaller side, but VIT base with 85 million parameters, it's already much larger, and it does require much more resources. So. And just to give you, I guess, a preview of what is happening in terms of the validation for these tasks. In some cases, it's better. In some cases, about the same. In some cases, it's worse. So, yeah, I will include this, I guess, future iterations of the work. Additional strategies we want to explore. Dino V2 super popular, much more resource hungry than Dino. So not to see how we fare with that at this scale. I think more, very importantly, and I guess the reason why we started benchmarking, or I started benchmarking, is that we want to hopefully learn what works, what doesn't work, and maybe investigate other strategies. For example, self-supervised learning, I guess, is the easiest thing you can do because you don't need anything else, and you can scale it up quite easily. But there are other strategies that we're thinking about. And potentially in the future, you could even think of getting supervision straight from the pathology reports. And that is challenging for many reasons. You need to have a good way of representing the entire slide. And we're working on these things. So hopefully next time you invite me, I will have some results on these other things as well. Another future direction is that I'm investigating biases. I think this is one of the strengths that we have here at Mount Sinai, is that we're in New York. We're the largest institution in New York, and New York is one of the most diverse cities in the world. And as such, Sinai has a very diverse patient population compared to any other institution, probably. Definitely in New York. And so I come from MSK, where over 90% of the patient population was white. Mount Sinai, the situation is quite different. We have a good representation of the diversity that is that you observe in New York, and so we want to really put this as part of a larger project that we have investigating all kinds of biases in computational pathology, which I think is interesting. And I guess finally, in terms of future direction, is how do we get these things to the public, to the research community, so that they can be useful and they're not, a product of a company, or locked up by the intellectual property side of the healthcare for profit business model in the United States. It's challenging, and we don't know exactly yet how this is going to work, but this is sort of our idea so far. The model is never going to be released because it's trained on clinical data, which is the whole point, I guess. But because of that, it's not likely that it will ever be released, or any models that is trained on data from a hospital in the US probably never be released, the weights directly. The data even less so. So our idea is to develop a platform for embedding, where you can just make an API call and you get back embeddings, and hopefully also for benchmarking, so that you can load your own model and then have a result on our clinically relevant downstream tasks. And it will, in best case scenario, be hosted on the cloud, and then we just develop an API that for easy interaction with these models and data sets. And there are, of course, many challenges in doing that. Also, cloud computing is very costly. And we're talking to various vendors and see. I think we were going to be able to do this, but there's going to be a lot of work before this becomes a reality. But I'm hopeful. And that was the end of my speech. I wanted to introduce and thank my lab, Fuchs lab, Thomas, my mentor for many years. His lab, we do computational pathology. We do all kinds of things related to pathology, diagnostics, prognosis, frameworks for large-scale machine learning, AI experiments, but also now at Sinai, looking beyond just pathology and bringing other data modalities in, which is something that is very exciting. We are located on Mount Sinai in the main hospital. That's a view of our spaces. We have 2 spaces. Our new AI building is opening soon, which is exciting. It shows also the commitment of the institution to be a leader in the AI space. We're right next to Central Park, which is quite nice in the summer. And we're in the Department of AI, which is led by Thomas. And I do want to say that it's just opened. So we're very new, expanding very aggressively, hiring. So if you know of interested people, could be a good experience. As I mentioned, lots of data, lots of modalities, diverse data sets. Yeah. And with that, I want to thank you, and very happy to get comments and questions and have a discussion.
Fantastic. Well, thank you very much for a really good talk. And yeah, with that, we'll open to questions. Does anyone in the room or online have any questions to start? Or alternatively, I'll start the questions. Brilliant. So, well, my first question was really related to, I know obviously a lot of the data is collected from Mount Sinai. So are they collected from is this big data set you've curated from various different scanners as well? Or is it, I'm just wondering how you expect, if you expect it to generalize well to new data sets and new, from new different centers, etc.
Very important question. So first of all, I should say, since these are clinical slides, they come from the FDA approved clinical scanners, in this case, the Philips scanners. So they're all Philips. And it is an important question to ask whether a scanner has an impact. So that's why I didn't include it here, but the downstream tasks are from a variety of scanners. We have the Philips, but also Imperio 82. And in new tasks that we're adding, also we have Hamamatsu and others. So we are including that. And I mean, this is, I guess, not something that is written anywhere, that haven't we haven't formalized, but from my experience, these models trained, these encoders trained with self-supervised learning on the Philips scanners actually generalize very, very well to other scanners, better than training a supervised model, for example, on one scanner and then see what happens on a different scanner. And it's something that we are thinking of formalizing better, and we have slides scanned, a cohort of slides scanned with 3 different scanners, same slides. So that's something that we'll probably put out somewhere at some point.
Okay, fantastic. Brilliant. So do we have any more questions from online or in the room? Just check the chat.
I guess I have a quick one. So all of these self-supervised learning models, they've mostly been designed kind of with natural images in mind. I'm wondering if you think there's any room for kind of tweaking these models or designing them with pathology images in mind, because they're obviously a fair bit different from natural images. Do you think there's any room for that?
Oh, absolutely. I mean, as I mentioned, that was one of the points, is seeing how well SSL does in pathology, with the idea of see what's better. And one thing is designing the pretext task for SSL that better reflects the characteristics of pathology images. But another option is to do something different, add all that, because we basically have supervision for these slides in the form of pathology reports, in the form of other clinical notes potentially. So I think it would be very interesting to see how that can be done at scale to get better encoders.
Cool. Thank you, brilliant. Thank you. So I've got quite a broad. So of course, 2023, we've seen a lot of, as this is the first seminar of 2024, in 2023, we've seen a lot of papers now coming out with foundation models and sort of a bit of a trade-off slash fight between models that are learning to, sort of your natural language models that are trying to take images and text combined, such as like Conch and PLIP and various other models, versus these just large self-supervised learning trained models such as yours and Virtuo. So what do you think will be the main direction for 2024? Or is it just getting bigger and bigger models, more and more data? Or is it, as you just sort of discussed then with Mark, about getting more bespoke models that might be better for pathology data?
That's a hard question. One thing about that I would say is that I've always, I guess, been skeptical of the bigger in terms of models. We've seen, I mean, from experience in pathology, most people use much smaller models than the computer, the natural image computer vision literature. So a lot of the work is ResNet 50, which is tiny if you compare it to VIT 22 billion or whatever is the largest nowadays. And so I think that's probably is gonna hold true. I mean, also if you look at the large language model craze that you were mentioning, where you have GPT-4, that it's very large, but then you also get all these models open that are much smaller and still very useful. So larger always better. I don't know if that's the case in general in terms of models. Then in terms of data, I think yes, larger is always better, and that is just how it is, I guess. Nothing beats just observing the data, observing what the true distribution of data is. And I don't know, what was the question? Oh, what's going to happen in 2024?
Yeah.
I don't know. I know that our labs focused on studying what's beyond self-supervised learning and going and pushing the boundaries of data set size that can be analyzed. And I'm very excited to see what everybody else is doing. And I think in the end, it's good because we'll be able to develop something that helps patients, hopefully, and it's not a chatbot that may have limited use in practice.
Right. Well, thank you very much. And if there's no more questions online, I'll just ask one quick last question before we finish up. So obviously, VIT small was taken with Dyno was taken about 17 days or so for your 3 billion images. So and now you're using VIT base. Was that was it much longer to use the model to train?
It is much longer, but I guess the idea is to throw more GPUs at it. And one thing I didn't mention is that for this we pre-tiled, which it's all right. I mean, it's already quite challenging. HPC people weren't super happy that I generated 3.5 billion files. It's quite a load on the file system. And
is that about terabytes data or something? What was it? A couple of how much data was the?
Sorry.
What sort of memory was it?
It was over 100 terabytes
over 100?
of JPEGs. But I mean, that's not as much the issue as it's 3.5 billion files. And so you have to be careful how you do that. It's parallelized over, the entire cluster to produce them. And it doesn't scale up very well. So we're going to change that. So basically, we're going to extract tiles on the fly. And that's going to allow us to be able to scale up much more in the next iterations. And which potentially has the trade-off of slower speeds, but actually we've done a lot of benchmarking. I think we can keep the same speed also with on the fly data IO.
Brilliant. Well, thank you very much for a really interesting talk and for giving your time for us.
Absolutely. Thank you very much.
And yeah, best of luck with your future work, and we're looking forward to seeing what the next paper will be. And just a reminder to everyone else online and in the room, we've got a next seminar coming up next week on Monday, the 22nd of January, at the same time from 2 till 3, where we're pleased to be joined by Dr. Asma Ibrahim from the University of Nottingham. So hopefully see you all there. But thanks again, Gabriele, for a really interesting talk, and best of luck with your future work.
Likewise. Thank you very much. Have a good rest of your day.
Thank you. You too.
Bye-bye.
See ya.